Do. Hello. Thanks for coming to our second GeoOnsdag of 2026. So we had, the first one was last month on seamounts. I don't remember what, the next one is on planets, but today we're talking about avalanches. I was looking at the news this morning, I don't know if you've heard this, but this huge, I guess one of the largest glaciers in the world is drifting away from Antarctica. This is A23A, and this thing is melting and breaking up, and so it's so that was perfect with today's theme. And so our speaker today is Andreas Kääb from the section for geography and hydrology, and he is somebody who's been studying glaciers and landslides and rivers and so forth for a long time. So I read this from his page. He says his main research interests are in monitoring, understanding cold region processes, such as glaciers, permafrost, river flow, climate change impacts, and natural hazards related to them. And one of his specialties is to use observations, particularly from satellites. So this is something which is growing a lot. I mean, you hear a lot about the satellites that are going up for communications, but also, I mean, for us, this has been a revolution in the field that we have in the last 30 years, that we have now these observations where we can see the surface of the Earth. And so it's had a huge impact, also on oceanography, so my field. Yeah, so, and I could tell you a lot more about Andy, all his awards and so forth. Yeah, and he's one of the stars in our department. But also a genuinely great guy. So I want to hand over to Andy and let him take it.
Thanks so much, Joe. Yeah. I will talk about rock ice avalanches. This is a process that is not so super well known, but in my opinion, it's the most mobile, the most violent, by far most violent high mountain hazard I know. To start with, I will guide you through some examples in the Caucasus, northern and southern side of the Caucasus, Alaska, Switzerland, India, and a word on Huascarán in Peru. So for me, this process, this experience started 2002 at Kolka Glacier in the northern part of Caucasus. There in 2002, a huge mass came down a valley with speeds up to 300 kilometers per hour. We know that from cutting of this mass through hydropower cables. We know exactly how fast it was. This avalanche went 18 kilometers. It crashed then against this mountain here. So this mountain, from the point where the image is taken, this mountain in the back is actually 15 kilometers or 16 kilometers far. It crashed there, it deposited 130 million cubic meter of ice and rock. 100 million cubic meter, this is the mass. If you put it on freight wagons, it would be a train of 15,000 kilometers from here to Sydney. So this would be the train to transport this mass. Once this mass crashed against this mountain, it ejected a mud flow that traveled another 15 kilometers. So in total, 125 people were killed in this event. A smaller event happened on the other side of the Caucasus, in Georgia. Shovi is the place. A very nice, attractive, and much used vacations place. You see at the lower right, you see how it looked before this mud flow. A mud flow traveled 11 kilometers and killed actually 33 people in 2023. I have a video from social media which shows actually during the event it cleared off huge amounts, thousands of trees in the valley, huge trees that were standing there for a long time. The event started from this mountain here, and it started as a small, medium-sized rock avalanche of 500,000 cubic meter, but at the village of Shovi, actually, they ended up 5 million cubic meters. So all the rest of material was ice, debris, trees carried away on the way. So multiplication by the factor of 10 on the way. This is a video of ice river or an ice avalanche, a very comparable slow one in Alaska, Flat Creek, very remote place where by chance actually pilot flew over. So it's fascinating in itself. But if you take a closer look, you will also see that the valley to the right and left is completely cleared off of trees. Because this avalanche that you see here is just a smaller aftershock, so to say, a side event after much bigger events, 2013 and 15, where ice and rock avalanche cleared off the entire valley, all trees, all small topography. So what you see here is just a small event after the big events. 2017, you might have remembered that from the news, a rock ice avalanche actually covered by a satellite when flying over. So you see a satellite image of the avalanche while it started, and you see the after. You see that the entire valley is cleared off here, all vegetation gone. And the village of Bondo was in parts destroyed, 8 people died, so it was an event of 4 million cubic meter. You certainly have heard about this Platten event, early 25, where 10 million cubic meter of rock and ice destroyed an entire village, the village of Platten. We had in GeoHeat, we had a talk about this event in detail. Only one person was killed, which is really remarkable, given that the entire village, where hundreds of people live, actually was destroyed. They were all evacuated in time. And finally, the Chamoli event in northern India. So the example from the entire trace of the avalanche is from a hydropower construction site. India really puts massive efforts in building hydropower in the Himalayas. So this is one site where they constructed or began to construct a dam. And below, these are 2 stills of handy videos taken. So these are big houses, construction site, and you see in these 2 images, you see how a huge violent mud flow swiped down the valley, many, many tens of kilometers, clearing off everything on its way. So all these examples that I showed you now have one thing in common. They are combined avalanches of rock and ice. We have pure rock avalanches and we have pure ice avalanches, but the combination of rock and ice makes these avalanches especially far-reaching, especially violent and mobile. There are many reasons for that. For instance, liquefaction of ice. During the fall, the rock crashes the ice, it liquefies, so it gets to water. Also, reduction of friction at the base of the rock avalanche make them reach afar. And a number of other processes. For instance, these avalanches often take up material, water-saturated material on its way. For instance, in creeks and rivers where you have very water-saturated material, they take it with them, even lakes. So these combinations of rock, ice, and water makes these avalanches so violent, large, and mobile. In general, there are 2 types how this rock-ice combinations start. The one is, an example would be this Caucasus event that I showed at the very beginning. This is where it started. It started with rock avalanches, actually repeat rock avalanches or rock falls from this slope here onto a glacier. And after a while, after some days, this glacier became so weak that it detached completely, and then it went down here and around this corner where you saw the first image. It slid down the valley. So this is rock on glacier. This is also something that happened, for instance, in the Chauvi event on the other side of the Caucasus. Also the Platten event in Switzerland was something like that. Rock avalanches, rock falls on a glacier until it becomes too weak. The other combination is a glacier on top of a rock avalanche or rock. So this is the Chamoli event, so the last one that I introduced you. So it was actually a rock failure, a wedge of rock failed, 20 million cubic meters or so. But this rock had actually a glacier on top. So this is how this combination of rock and ice started. So the thing that makes this avalanche so violent is the combination of rock and ice, and it's the liquefaction of the ice during the fall. So in this, more or less my only strictly scientific figure, if we plot here the average fall distance, so the vertical distance from where the avalanche started to its end. This is plotted here, and here you have the ratio between rock and ice. So down here we will have pure ice avalanches, and up here you will have rock avalanches. Depending on the height, so the energy can be converted, so the potential energy can be converted in melt energy and melt. So above these red or blue lines, above this line, all ice can be melted. Below this line, not all ice can be melted. So, for instance, here, I need my glasses to read it by myself. So here, you can melt all ice, and you can transform the entire mass into a debris flow. A debris flow has a certain percentage of rock and water, and this percentage is something like 0.8 or so. So if we combine all that, then we end up in this area here. So scientifically, you'd call it the sweet spot. It's actually not a sweet spot. It's a very sour spot. It's a spot or the area where a certain fall height and a certain partition of ice to rock makes it possible that the entire ice content melts and is so much water that the entire rock mass can transform into a debris flow. So this is where it becomes most violent. And this is exactly where the Chamonix event is, and I'm pretty sure we didn't calculate it yet, the Chauvet event and so on. There are some events that are exactly in this sour spot where all the ice melts and can liquefy or transport or transform all rock mass into a debris flow. So this is the worst case scenario. If I plot all the rock and ice avalanches we know today, in this figure here, you see the horizontal reach. So how far can it reach? So 20 kilometers for the Kolka event I started with. And the fall height, now to the left axis. And the size of the event is the size of these gray circles. Then you see distribution of rock ice avalanches globally. The red ones are the ones that are introduced so far. You see Kolka here, Bondo, Changalo, Blatten, Flat Creek, Chamonix at the end. And I did not show details of Huascaran, which is really on the upper right here. It's Huascaran event, 1970. It was a rock fall on a glacier, and then the entire cascade starts, where actually 10,000 people died in Peru. So when you look at this figure, you notice with some little bit of fantasy that the big circles are at the very lower end. So this is where the angle of reach is really flattest. So these are the ones that go on surprisingly flat terrain. So these big ones are all the same type. All the blue ones are special type of these rock ice avalanches with very much ice and little rock. This contradicts a little bit what I said before, that actually this mixture makes a difference. So in these glacier detachments, where entire parts of glaciers shear off, other effects come into play. We don't know actually what it is, but one reasonable explanation is that these large ice masses have the potential to trap air, and then they slide on air. And this one confirmation of this idea is that people close to Kolka Carmadon, so the event that I showed at the beginning, this happened during night, and there were people actually living very close they woke up, but they say it sounded like a very distant train. So even they were only a few hundred meters from the event, it sounded like a train. So this could be a hint that actually it's really trapped air in this big mass that makes this glacier detachments reach especially far. I will show you and discuss a bit some of these glacier detachments. Kolka already introduced. We will go to Aru on the Tibet Plateau, Sedongpu, and Bukadaban, all on the Tibetan Plateau, even if you find such events in almost all continents. Aru 2016, two boringly flat glaciers you could easily walk on, you could almost not ski on, right? It would be, or mountain skiing, randomly. It's almost too flat to ski, right? These two glaciers from above, from a satellite. Then in July 2016, one of these glaciers suddenly sheared off, traveled several kilometers into a lake and killed actually 9 people and hundreds of their animals, yak and so on. They had their summer camp somewhere here. A few months later, suddenly in September, the second glacier sheared off. To give you a bit of a feeling of the dimension of these events, here you see the Japanese authorities digging for people, of course, completely hopeless, but it was done. So this is a small part of the margin of the first avalanche. So you see the size, dimension of this event. A colleague took this photo from the detachment zone of the first glacier. Bit hard to imagine the size, so I copied in the city hall, or actually the administration building here. Really huge if you imagine that an entire glacier shears off. If I let the avalanche start at Holmenkollen, gives you a bit of feeling how far it would reach. So if the avalanche starts at Holmenkollen, it would both reach the Opera and Karl Berners-Platz, for instance. So large parts of Oslo would be completely covered and destroyed by this avalanche. So this Aru event was here. We go now to Sedongpu, which is here. This is where the Brahmaputra River leaves the Tibetan Plateau, which makes the site very attractive for hydropower constructions, by the way. So this is how this site looked in 2016, a very high peak, Brahmaputra running here, 4,500 meter fall directly from the peak to the bottom. So it's one of the largest rock faces I know. So there was a glacier, again, a boringly flat, debris-covered glacier. A few years later, instead of this glacier, there's a huge canyon. You will see it's actually 300 meter deep. The glacier has gone, So this was a series of events. 2016, before these events started. 2017, there was a substantial rock avalanche that went over this glacier here, but didn't do something with the glacier. Then 2018, the entire glacier sheared off, actually in 2 parts. It dammed up the Brahmaputra River. You will see 2 images. And then in 2021, within 3 months, a huge canyon eroded suddenly. I'll show you an image after the 2018 glacier detachment. So it came from the left, dammed up the Brahmaputra River for several days. This is an image from below, so you see the avalanche deposits. So for about a week, you could have walked over the Brahmaputra River without getting wet feet. So this is extreme. This erosion in 2021, I show you in height profiles. So this is the upper part of glacier. Down here, this is Brahmaputra, or Yalungtsangpo, as it's called here. The blue line is the topography before the glacier detachment. From the blue to the red line, this is this glacier detachment, where the glacier went off. And then in 3 months, in summer 2021, all this red height actually eroded. For scale, you see the Oslo Plaza here, very tiny. And it's more or less exactly the height of Eiffel Tower. It's the erosion. This erosion here in the cross-section, across here, this erosion happened very smoothly. There are seismic instruments close by that didn't record anything. So it was a constant, more or less constant, soft removal of soft sediments into the Brahmaputra River. It also did not dam up the Brahmaputra River because the Brahmaputra River, because of the amount of water and the slope, has at this place one of the highest stream powers on Earth. So it really has the potential to carry everything away. Again, to demonstrate a bit the scale, so this erosion within 3 months was 300 million cubic meters. So if I form a block of sediments of that, and you see here Oslo, Opera, and so on, there would be this block. It would mean every day, these 3 blocks, every day transported into Brahmaputra River. And if I sum up all the events over these 3-4 years, so the initial rock avalanche, glacier avalanche, some more rock avalanches, and this erosion, then it's 0.6 cubic kilometers. The last event I would like to show you is happened in November 22, in really far away from where people live. My Chinese colleagues told me it's even difficult for them to get there because of permissions and so on. So it happened from an ice cap, a typical ice cap on the Tibetan Plateau. Here you see an oblique satellite image of the site. Then suddenly on 1st of November 22, this entire glacier tongue detached into a lake, caused a tsunami. But of course, nobody cares about the tsunami there. So the entire glacier tongue that detached was 1.1 kilometer long. You see, again, Oslo Plaza, a scale, roughly. So it went 4.5 kilometers, and this gives a slope of 4.95. This is roughly, it's more or less exactly the slope from Kringsjær to Ullevål Stadion. So from Kringsjær to Ullevål Stadion, so this is the slope where this avalanche went. If I let again this avalanche start at Holmenkollen, also there actually the slope dimensions are roughly correct, then it would reach Skøyen, almost Bygdøy. This is a high-resolution satellite image of this detachment in Bukodaban, so the last one I mentioned. And this leads me to wrapping up. So I talked about rock ice avalanches, and one can say a special case, these glacier detachments. So these rock ice avalanches are very mobile, very violent, able to change the volume on the way massively, up to a factor of 10, as you have seen with the Shovi event. They are especially far-reaching because of the water content, because of the reduced friction through the ice content of transformed water. So the liquefaction and reduced friction is really what makes them so far-reaching and violent and mobile. One could say if you know one rock ice avalanche, then you know one rock ice avalanche, because in many of these cases, it's different process interaction, different cascades. There are some more or less typical, but all these cases are somehow special, which makes them very hard to anticipate actually what can happen. So we talk about especially rock ice avalanches, but especially these glacier detachments. We talk about every few years a big event of 200, 300,000 glaciers on the world. So it's very unlikely it will happen. So one can easily end up with some worst-case scenarios that will cover entire countries, right? If you go for worst-case scenarios, for instance, Switzerland, it would not be possible to live actually in Switzerland if you really go for worst-case scenarios. and parts of Norway. So it's a typical low-frequency, high-magnitude event, which are the most difficult ones to handle in hazard management. The glacial detachments, the interesting, or I would say the fundamental thing is the sheer possibility of a boringly flat glacier to completely shear off. This is hard to imagine. And as I said, it happens extremely seldom, but it happens. It's not given at all that this happens only in areas where few people live. So we have a number of examples where it happened also where people live. These events have exceptionally low angles of reach, most likely due to volume effects, for instance, trapping of air. We know from almost all cases that either the glaciers itself showed sometimes signs of glacier surging, or there were surging glaciers around. So one could say these glacial detachments are an end member of surging, or the spectrum of glacier surging. In many cases, not all, there are some hints or even proofs of soft beds, very fine sediments underneath the glacier. And more recently, in retrospect, we sometimes find that, or often find that a few days, sometimes even weeks before, we could have detected an increased glacier speed, right? So that don't happen completely out of the blue. So there's a glacier acceleration of at least a few days. So, which makes it in principle possible to perhaps anticipate or forecast, but it would require a very dense monitoring and an early detection where at all you should look at this. Yeah, so this work is not done only by myself. So in the department, Desiree, Judita, Luc, Adrien are involved, and internationally it's a working group. It's called GAPAS, Glacier and Permafrost Hazards in High Mountains, where a group of people, 1-2 dozen, actually work together and share data and information about these events and build up a database that should help us to better understand these events, and if we are very lucky in one case or two cases, perhaps to early recognize. Like in the Platten event, so it was early recognized that this could be a possible cascade. The event was larger than anticipated in Platten, but it was roughly anticipated what can happen, and this led to the evacuation of Platten. Thanks so much.
There? Okay, yeah, thanks a lot. Okay, great. Nice talk. We have time for some questions, and we have one eager questioner, Bernd.
Hi, nice talk. Very, very good. I have two questions, actually. First of all, have you observed an increased frequency of these events the last decades or so in relation to before, maybe? And the second one is related to this sediment erosion, which was which came a couple of years after the event, and then it eroded. Why?
Yeah, so the first question, is there perhaps an increase in frequency? So many of these events we detected only because of satellites. So we simply don't know. Meanwhile, we find some traces of potential former events, but at least this sample. So in total, we know between 1 and 2 dozen events globally. So the statistics are simply not there to say that. But your question implies somehow, could climate change the frequency, right? And to answer directly to this question that you didn't ask, but perhaps mean, so climate change is certainly involved in some of the processes, right? For instance, in the extreme case, if there's no glacier because it's melted, then you cannot have this combination. A number of cases, for instance, Kolka, but also Shovi and others, actually thawing permafrost in rock walls, both most likely involved in at least triggering the rock avalanche that caused this. And so climate change has the possibility to increase the frequency, but some other parts of these process chains I showed you do not have anything to do with climate change, right? If there's a glacier, there's a glacier. If it erodes, then riverbeds, trees, and so on. Yeah, so there could be an increase in frequency because of climate changing the glacial and periglacial environment. Yes. Second question was this huge erosion. Why did it happen with 2 years after the glacier detached? So first of all, I'm pretty sure this huge erosion was because of the glacier cover was gone, right? So the glacier was in a way protecting against erosion. It was not a cold glacier, completely warm, so the water did also reach underneath the glacier, pretty sure. But it's the place there. It's not. It's already at the inner side of the Himalayan arch, so it's not super wet, but it's also not a dry place at all. So it could well be that there were perhaps in the sediments some ice remains from earlier times that melted, so even under non-permafrost conditions. It might simply be it took so long to get all this mass saturated with rain. So I think there are several possibilities that could explain this delay. Actually, it would have been super surprising if it happened just a week after the glacial detachment, right? I would say. But once it started, it went very fast, right? So it started with a retrogressive erosion somewhere at the bottom of the slope, and then within 3 months, it ate its way up. Yeah.
Great. More questions? Vincent.
Hi, super interesting. You mentioned hydropower. Is there, I can imagine if I want to plan and build a hydro plant somewhere, is this something that you need to take into consideration? Are there certain areas where you go, oh, this is way too active, this would be impossible, or?
Yeah, so this is actually a tricky question, and especially the Chamoli event was actually discussed also much in this. We said, so this team that worked on that, we said Chamoli is a good example for the limits between progress and conservation. So this is, if you see this violent mud flow, which was especially violent, but still similar things happen elsewhere in the Himalaya. So at some point, and it's really more or less a height limit or interval mass, it might simply not be feasible, right? There is also a discussion to what extent, in that case India, should better observe this, right? And it depends a bit on the financing, actually, if money comes from the World Bank or not, who puts constraints on that. So what makes the thing even more tricky, right? What India does, it replaces fossil fuels with renewable, right? So it's not a bad thing, so to say, and they have huge energy demand. So there's some interest, some motivation to go high up and capture heavy. So, but there are studies that actually try to model the potential for these events and overlay it with hydropower plants. And there is some intersection, yeah. So, yeah, so it's a problem. It's not something we should put the finger on. Yeah, ooh, you're stupid. You do that. So there is a very strong motivation and need for this type of energy. Yeah. Yeah.
Yeah, Trude.
Hi, thanks for a great talk. I was curious about these precursors to these avalanches when you have rock slides, sometimes quite a bit earlier than the actual kind of mudslides. Is it the mass loading of the rocks that causes this? And can that also be used then as a sort of a early prediction if you see that you've big rock slides prior to it?
So the first time, it's now really in very detailed investigated. This is a Platten event, so these studies are not yet finished, but you know they had data there, so there's a lot of data, much more than the Kolka event, that was a similar thing. So it's a mass loading, but it's also most likely a hydrological impact, right? So the mass loading could then, it's not only the mass itself, but it stops, for instance, infiltration or reroutes water. So a combination, I would say, of direct force and hydrological combinations. It could also be a bit long-term, right, because the albedo changes, so suddenly you get in some places perhaps more melt, in some places less. Yeah. Combination of water and weight, I would say. The prediction. Yeah, so it is. So my basic motivation to work with these events is really the hope to make the specialists working with that aware that if you see that, then this and this might happen. So simply the fact that increased avalanching, rock avalanching on a glacier is not just a more or less nice thing or a less nice thing. So that is depending on the geometry of the glacier. So it could, if it's more and more, it could bear the potential for a bigger event following. So this is, I wouldn't say prediction is possible because you have many rock avalanches on glaciers where nothing happens. Actually, most. Alaska is full of rock avalanches on glaciers where they don't shear off. But simply the potential is there, right, on the awareness. And if you depends then on vulnerability. So if you have people living below, then you should perhaps look a bit closer, yeah. But not prediction.
Thanks for the great talk. I was wondering about these very low angle glacier detachments where there hasn't been rockfall in advance. Do we have any idea why suddenly a large part of the glacier just detaches? What triggers that?
You mean after rock loading?
No, but like in the case that we don't have the rock loading and the really shallow ones you showed towards the end, where they just suddenly detach, do we know why that happens?
So we see, also there, we see actually different processes perhaps leading to the same end. So for instance, in the Aru case and the Bukadabans, both on the Tibetan plateau, partially frozen glacier margins might have played a role, right? So especially for the last one I showed, it is clear from the data that the very glacier tongue, where the ice is thinner and not flowing so much, it actually can get cold because Tibet is a very cold place. So it gets the very tongue gets frozen to the ground, whereas the upper parts perhaps surge or receive more meltwater. Then the glacier gets faster, not much, but still a bit faster, but it cannot really release this force. So it's dammed up. And this dam is a mechanical dam against the ice. It's also a hydrological dam because the meltwater cannot escape through cold ice. It would refreeze. So it's the so-called polythermal structure, so this structure of cold ice and warm ice. Warm ice is actually 0 degrees, but there's much colder ice. Can play a role. Then also for some of the cases, we think that actually the very soft sediments below, if they get water saturated, they get very smooth and liquid. So you know that, like for instance, for quicksand or so, you can, from a certain water pressure, water content, it can be super soft and liquid. And this could be the moment where, for instance, water could not drain out underneath the glacier, but accumulate in the soft sediments. So it's a combination. And as I said, if you know one rock ice avalanche, you know one rock ice avalanche. So it's some of the ideas we have for processes work for several, but certainly not for the one case or the other case. So it's a very complex interaction and cascades of processes.
Oh, I just talk, okay. So for the Norwegian audience, could this happen here in Norway? Should we be afraid?
Yeah, if I showed up two frequently asked questions, then climate change that I answered Bernd without him asking that, and the other one would be this. So it's a very rare event, right? So there are 100,000 of glaciers, and this happened 1-2 dozen times. So it's very, very unlikely. I also said that it's different processes that play together. It's not one simple chain of processes. For instance, if you take that glaciers where this happened surged, so you will see mainland Norway is not the most likely place. Very unlikely. Also, for many of these glaciers, we think there are soft beds. For some, we know very sure. Also, this is not so much the case in mainland Norway. Yeah, so in mainland Norway, I would be very surprised, very, very surprised. So, but many of these events came somehow as a surprise. So I should also say, it's always in retrospect, one is smarter.
I have two things, and one is a continuation of your question. The geologic record should pick up if you have had a lot of rock ice avalanches in Norway. So most of the have been rock slides.
Yeah, exactly.
So that should be a lower possibility, perhaps.
Mm.
The other thing was the erosion, this very fast erosion. Was it any power station downstream that picked up this huge sediment flux?
Mm-hmm. So the first question about the record. We recorded now some of these events and see, for especially the older ones, we see how it looks now. We wouldn't have guessed that there was a rock ice avalanche, right? Because it's often these fine sediments or this collision of rocks makes it very fine sediments. So for some events, for instance, this Auro, you wouldn't have guessed there was a few years ago such avalanche. On the other hand, we see also sometimes now traces that look like that. I know one very case where I saw such. I put it in the paper. This looks a bit strange. And before I even managed to submit the paper, there was actually a rock ice avalanche. It's very few cases actually where some landforms look like that. But again, other way around, you would falsely map many landforms as potential rock ice avalanches that were not in most cases actually. Your second question was the sediment flux. I'm pretty sure it was recorded because in the satellite image you see this sediment flux far down. Meanwhile, I think there's a Chinese paper that even talks about this accumulated sediments or increased sandbanks far down. So it was, people noticed it, right? Also, when you use the river, and suddenly it's 3 months is super dirty. And one interesting question is actually roughly 100 kilometer down, the river length down. This is where this immense hydropower dam is planned by China, just above the border to Bangladesh. So this is the three gorges dam would be a small thing against that. So they will. I think they know they will have to cope with huge amounts of sediments, even on the less extreme events. So they will have a strategy to clear off how. But all these hydropower installations, including the turbines, they have to cope with millions and millions and millions of sediments going through the system.
Great. Okay. Lots of questions. Very good. Thanks very much to our speaker. We'll be having another GeoOnsdag in a month. Make sure to bring your friends so we can fill up the seats. And we'll see you then.
Thanks for coming.
And thanks for coming.